Good morning. Make sure you have this sheet in front of you as we begin. Today we'll be using the reciprocal identities, the quotient identities, and the Pythagorean identities that we saw in yesterday, along with some old algebraic techniques we should remember, working with fractions, factoring, and multiplying by conjugates to help us show that two expressions are equivalent in trigonometry. So the first one, we want to prove that tan squared x plus 1 over cosecant squared x minus 1 equals secant squared x tangent squared x. Through Pythagorean identities, I can rewrite the left side as secant squared x over cotangent squared x, and I'm keeping the right side as secant squared x tangent squared x. Remember to only work with one side of the equation. I can then rewrite the left side as secant squared x times 1 over cotangent squared x, keeping the right side secant squared x tangent squared x. I know that 1 over cotangent squared is just the reciprocal of tangent squared, so that tells me on the left side that secant squared x tangent squared x does in fact equal what I see on the right side, secant squared x tangent squared x. So that's just using quotient and reciprocal identities. So I've proven what I wanted to show here, working only on the right hand side. Oh, excuse me, working only on the left hand side, keeping the right hand side the same. The next part, we know that when working with a fraction, sometimes we forget what to do. Keep in mind, when adding and subtracting fractions, you have to have a common denominator. If you don't have a common denominator, you have to make one, creating new fractions. Multiplying fractions, we go across the top with multiplying, across the bottom with multiplying. We can divide on the diagonals to simplify. With dividing, we multiply by the reciprocal. So this next one, we want to show that secant squared x over cotangent x plus tangent x equals sine x. So the first thing I'm actually going to do is change all of these to either their reciprocal identities or their quotient identities. So secant x is the same as 1 over cosine x. In the denominator, cotangent x is the same as cosine x over sine x. And tangent x is the same as sine x over cosine x. And I want to show that that's equal to sine x. Where I'm going to go from here is to make a common denominator for our fraction that's actually in the denominator. So cosine x over sine x plus sine x over cosine x. My common denominator would be sine x cosine x. If I want to create a new fraction, the first fraction is missing cosine from its denominator. So I'll multiply top and bottom by cosine, which will give me cosine squared x. In the second fraction, sine x over cosine x, its denominator is missing sine. So when I multiply both top and bottom by sine x, I'm adding sine squared x. The numerator is still 1 over cosine x. And I want to show that this is equal to sine x. Need a little more space here, so I'm going to group these together, make them a little smaller so we have some room. Pythagorean identity tells me that cosine squared x plus sine squared x is just 1. So I have 1 over cosine x times sine x cosine x over 1. Try that again so you can see it clearly. Sine x cosine x all over 1. And what happened here was this. Cosine x plus sine squared x equals 1. So I'm taking 1 over cosine x, dividing by 1 over sine x cosine x. I can multiply by the reciprocal. Keeping the right-hand side the same. Trying to show that the left does actually equal sine x. Now I can simplify cosine x with cosine x by dividing common denominators in both the numerator and the denominator. Those will leave the number 1. So 1 times sine x times 1 divided by 1 times 1 just gives me sine x. So I have sine x equals sine x. Done with that one. The next one will also require use of lots of different stuff. Let's go with tangent x. We'll change that to sine x over cosine x minus sine x. In the denominator, we're going to change tangent to sine x over cosine x as well, and that's multiplied by sine x. My goal is to show that this equals 1 minus cosine x over sine x. If I create a common denominator in the numerator and make equivalent fractions, I'll have sine x minus sine x cosine x all over cosine x. And that is over the entire denominator, which will be sine squared x over cosine x. And my goal is to show that that equals 1 minus cosine x over sine x. From here, I can multiply by the reciprocal, which would give me sine x minus sine x cosine x all over sine squared x. When I multiply by the reciprocal, the cosines will cancel each other out. Again, keeping the right side constant. Now, take a look here. These are two terms. They both have sine x in common, so I can factor sine x out. And in the denominator, I have sine squared x. Pay attention to the fact that I'm continuing to bring the right side down. You have to do the same thing. Now, sine squared x means sine x times sine x. So one sine x in the numerator will cancel with one of the sine x's in the denominator, which eventually gets rid of the squared power. So now I have 1 minus cosine x over sine x equals 1 minus cosine x over sine x, and my job is done. Now, I will tell you that it took me a couple of different tries to do this on my own. You have to be willing to be wrong and be willing to start over if the time calls for it. So don't be too bogged down by that. All right, another technique we can use is factoring. I'm actually going to go to another page for this because it seems like I'm running out of room here. So with factoring, we want to show that secant x raised to the fourth minus 1 is the same as sine squared x plus sine squared x cosine squared x over cosine of x raised to the fourth power. You can say cosine to the fourth of x, which sounds weird to me, but if you understand it that way, that's fine. Now, I work with the fraction side. To me, it's going to be a little bit easier to show that the fraction is going to equal a single expression rather than showing a single expression will equal a fraction. So, my first step, remember this is using factoring. Notice that each of these terms have a sine squared. So, I'll keep the left side constant this time. I'll factor out sine squared x. That gives me 1 plus cosine squared x in the numerator. In the denominator, I have cosine fourth of x, or cosine x to the fourth. Cosine of x to the fourth. From there, I'm going to separate this out. Now what I'm going to do here is separate this out. Anytime I'm multiplying two numerators together, I can give each numerator its own denominator. So I can make this sine squared x over cosine to the fourth x times 1 plus cosine squared x over cosine to the fourth x. Now this is going to be actually pretty interesting. I can't do this. Let's go back and do this again. I can make this sine squared x over cosine squared x. There we go. Over 1 plus cosine squared x over cosine squared x. That way when I multiply the denominators back together, I get cosine x to the fourth, or cosine to the fourth of x. And then I can make some interesting changes here. I can keep this as secant to the fourth x minus 1. Sine squared over cosine squared is one of our quotient reciprocals. This is tangent squared x. Then I can separate the addition. 1 over cosine squared x plus cosine squared x over cosine squared x. Addition allows me to do that. Left side remains constant. Right side becomes tangent squared x times secant squared x for the reciprocal of cosine plus 1. Now, trig identity. What is tangent squared x equals? We know tangent squared x plus 1 equals secant squared, but if I subtract 1, then I can see that tangent squared x equals secant squared x minus 1. So on the left side, I still have that beautiful secant to the fourth of x minus 1. On the left side, this is a difference of two squares. If I consider this to be a minus b and this one to be a plus b, then multiplied I get a squared minus b squared. So if I multiply secant squared times secant squared, I get secant to the fourth of x. If I multiply negative 1 times positive 1, I get minus 1. And ta-da, I've proven it. Now you might say, Ms. Young, I wouldn't know to do that, and I would only be able to say back to you that you will have to come up with something that works. So you might start one way and figure out it's not working. I would say go another way. Again, this is one where I felt I had to start over myself. All right, the last one. Separate page for that one as well. This time we want to talk about conjugates. So keep in mind what a conjugate was. If I have a plus b I when we talked about complex numbers, then the conjugate was a minus bi. Now those were special because they did wonderful things for us, allowed us to not have middle terms and things like that. So we can apply the same thing. So looking at our last example, we have 1 plus cosine x all over sine x equals sine x all over 1 minus cosine x. So we want to show that one of these equals the other. I would recommend that we start on the side that has 1 minus cosine x in the denominator. And what we're going to do here is multiply by the conjugate. Just change the subtraction to addition. We have to be careful to multiply by the exact same thing on the top and bottom to preserve the value of the fraction. So on the left side, I have 1 plus cosine x over sine x equals. This is going to be a nice distributive property. Sine x plus sine x cosine x. In the denominator, we will have another difference of squares. So this becomes 1 minus cosine squared x. Left-hand side is the side that we're keeping the same. Right-hand side, what we're going to do first here is to factor out a sine x. And I just figured how silly that was. We could have done that in the first place. Oh well. Extra step. I apologize for that. In the denominator, we can use our Pythagorean identity. 1 minus cosine squared x will be the same as sine squared x. Again, keeping the left side constant. I can cancel on the right-hand side the sine x with one of the sine x's in the bottom. And that leaves me with 1 plus cosine x over sine x. So to me, this is like one big puzzle. I just have to figure out what works, what doesn't work, and when I figure it out, it makes me really happy because I've worked pretty hard. Now, if you look on the back, it starts to talk about equations. We will not deal with equations until the next unit, and so you should be ready to begin your classwork. You have to finish it all before you leave today. Whatever you don't finish, you're turning in anyway. Turn in everything that you finish, and you'll have a separate homework assignment. Make sure you work together and work hard on these, and I'll see you guys on Monday.